Okay, so now that we've introduced momentum, let's dig into some of the consequences of it. We're going to end up defining something called impulse, and then we'll look to see how these things interact during different kinds of motion. Momentum, we have already defined, is a property of moving things. It's an expression of inertia, but only for a moving object. Now, an object at rest also has inertia. If it's moving, then we can talk about momentum as a way to measure the inertia associated with its motion. This was our definition, that momentum is mass times velocity. So a boulder has more momentum than a stone at the same speed because the mass of the boulder is bigger. A boulder or a stone at rest, anything at rest, has zero momentum because mass times velocity. Yes, it has mass, but its velocity is zero. So if we find the product, the momentum is zero. Okay. We said that force equals momentum change divided by time. We could cross multiply both sides of that equation by the time, and we would end up multiplying on the force side by the time. Now, apart from it equaling the change in momentum, what we've got is the product of force acting for some amount of time. How much force for how much time is going to be related by Newton's second law to how much change was created in the motion of that object. But this idea, force applied over time, let's give it its own name. Let's call it impulse. A force applied for only a small interval of time produces a smaller change in the motion, in the momentum, than the same force applied for longer. Like if we have a rocket engine or a car and we slam our foot on the gas for 1 second, we're gonna speed up. But if we keep our foot for 2 seconds slammed on the gas, we will end up going faster by the end because we've got the same force from the engine applied for longer. So our motion, our momentum, will change greater the longer the force is applied. This thing, impulse, according to Newton's second law, is related to what we call the change in momentum. Again, if we divide both sides of this equation by time, we have the version that I wrote at the end of the video we just finished. Force equals change in momentum divided by time. So we multiply by time and we end up saying that impulse is equal to the change in the momentum. A force applied for some amount of time changes the motion. Okay, so to change the motion the greatest amount, act for longer. golfers and baseball players talk about following through with their swing. The reason we are supposed to follow through with our golf swing is to, as much as we can, lengthen the time that the club spends in contact with the ball, exerting a force on the ball. The longer that duration lasts, the more force, no, the more impulse is imparted to the ball. Same force, maybe, applied for longer. We might also be interested in lengthening the duration over which we reduce the momentum. We're not trying to get the golf ball to go farther by changing its motion more. Maybe we've got a runaway car. We hit a patch of ice or something. Would you rather hit a haystack or a wall? You might say the haystack, but why? Because as we smash through the haystack, all the hay goes in all kinds of different ways, but we spend more time slowing down than we do if we just hit the wall. We hit the wall and the wall doesn't go anywhere, we're done. And that collision, that interaction between the truck and the wall is of shorter duration than the collision with the haystack. Okay. But the truck was going the same speed at the beginning either way. So we have the same mass and velocity at the beginning. And we're going to reduce that to zero. We want to stop the motion of this car that's out of control. So we're going to need this we need to observe to produce the same change in momentum, which means we're going to need the same impulse. But if the collision doesn't last for as long when we hit the wall, we're going to need more force. And so our car and maybe ourselves or whoever's in the car is hurt more, is subject to a greater force because we don't have as much time to change the motion by imparting impulse. When you land, if we jump from a height and land, we bend our knees to extend the time during which we transition from falling with velocity to standing on the ground. Lengthening the time, decreasing the force. It's just like the truck colliding with the haystack. A boxer will turn so that somebody's fist spends more time in contact with their face, because the longer the time, and it's somebody's fist, right? So eventually that momentum, that forward momentum, is going to stop because, well, this boxer's face got in the way. But if we let that take more time, then there's less force that the boxer's face needs to exert on his opponent's hand in order to reduce the momentum, because we're taking more time to do it. If we shorten the time, because this trick works both ways, if we shorten the time of a collision during which we change the momentum of a thing, we produce a greater, we're going to end up with a greater force to get the same impulse. It's the swiftness of the chopping motion here that maximizes the force for a given impulse. Her hand is changing momentum regardless, according to the speed of her swing. But if we reduce the time that it spends in contact, we can maximize the force that is used to effect that change in momentum. A neat problem. If I have two balls, one of them is, I don't know, putty or Play-Doh or something, and the other one is rubber. If I have the door open slightly and I don't want to stand up, so I throw the ball at the door to knock it closed, which ball should I use? If I use the putty, it'll stick to the door. So the door imparted some impulse, enough impulse to stop the momentum of the ball. That's it. Which means however long the collision between the ball and the door lasted, the door was subject to that much force associated with how much force it used to stop the ball. But if I throw the rubber ball, it'll bounce. In other words, not only will it stop going that way, but it'll turn around and bounce back this way. So that's a greater change. Not only do we have to stop it, but then we have to push it the other way. That's more impulse in about the same amount of time, which means a greater force, which means I have a better shot of swinging the door closed with the bouncing ball, not the sticky one. If, let me go back a few slides. If the net force on an object or a collection of objects, if the net external force on an object is 0, then the left-hand side of this equation is 0, and that means the right-hand side must be also. And there is no change in the momentum of that object or system, which is what we call the conservation of momentum. Note that in this animation, the cannon is moving backwards while the cannonball is moving forwards. Initially, just before we fire the cannon, the total momentum of cannon and cannonball is 0. Neither is moving. But then, boom, we fire the cannon, and the cannonball goes forwards with some mass and velocity. So it has some momentum to the right on the page. In order for the total momentum before and after to be 0, the cannon has to be going back the other way, because remember, momentum cares about the direction. So if the cannonball has positive momentum, the cannon has to have negative momentum the other way. The forces are equal because Newton's third law, equal and opposite. If the cannon pushes on the cannonball, then an equal force acts back on the cannon. These forces are internal to the system, and I have no really good way of measuring how much force that is. So I don't want to do Newton's second law in the F equals ma kind of sense. But fire the cannon, if we can find the velocity of the cannonball, then I know its momentum. And if I know how much time the firing lasted for, then I can figure out how much force by talking about impulse instead of acceleration. When no external force is present, no external impulse is possible. And therefore, the momentum, the change, the triangle, the delta momentum has to be 0. Whatever momentum we had, we have to still have altogether. Forces internal to the system, between the pieces of the system, can't change the overall momentum of the system. I can't, from the driver's seat, push on the dash of my car and cause it to move because I'm in the car. I can't lift myself by my own shirt. I try it. I can't. It has to be external to the system in order to change the momentum. If there aren't any external forces, then we can talk about the conservation of momentum, the total momentum of the system, whatever objects there are, before the collision or the event or the explosion or whatever thing. We've got, the before and then the after. And the total momentum before has to be equal to the total momentum after if there aren't any net forces acting external to the system. There are different kinds of collisions. And here are 3 different cases of what's called an elastic collision, which means there's a rebound. We bounce back. The objects don't crumple or squish or deform in any way. We don't create, we don't emit a lot of heat or sound or anything. And the classic example of an elastic collision are the kinds of collisions that occur between billiard balls, pool balls. The balls themselves are very rigid, and we're not generally moving them quite fast enough to do anything other than, especially a slow collision between billiard balls, all we just hear a little click, and there's very little about the collision that has anything to do except that whatever momentum we have before, it gets to be the momentum we have afterwards. This is in contrast to an inelastic collision where there's, if the car hits the wall and the car crumbles up, all those crumple zones, right? If we physically change the shape of an object, that's not elastic. We didn't rebound, we squished. Or if one, cargo train car collides with another and they couple together and move as one object, that's another kind of inelastic collision. There's no rebound possible if they latch together. If we collide and generate a bunch of, if a bunch of sound is produced or a bunch of heat is released, then that's also an example of an inelastic collision. And once we talk about chapter 7, we can say a little bit more about what that means. But for now, elastic collisions mean rebound, just bounce off. Inelastic collisions are pretty much everything else. A single car moving at 10 meters per second collides with another one inelastically. They have the same mass, and they get sort of tangled up together during the collision. One fender gets stuck on another and they move together afterwards. Beforehand and afterhand. Before the collision, one car is moving with a velocity of 10. After the collision, two cars are moving with some new velocity, which if we cancel the mass on both sides, we can solve for the velocity after the collision by dividing both sides by 2 and ending up with 5. If it isn't just a straight line collision, then we might have to do a little bit more work. And because momentum is a vector quantity, then we can go back to think about the vector relationships. We can talk about the perpendicular momenta of these two cars. Car A is moving to the right, car B is moving up the page. And when they collide, the sum, the vector sum of the two momenta before and after needs to be the same. But if they fuse together, the only way we can have upness and rightness is if they go diagonally up and to the right. And it's the combination of these vector pieces, these vector components. We talked about the parallelogram method to combine vectors like this. And we'll have to chase down that analysis of how these two things at right angles combine to make a hypotenuse. Another example of a complicated collision, more complicated, say, than just one car colliding with a parked one and they move together. This is a falling firecracker that was lit and then explodes. So before it explodes, it had some downward momentum. Then after the explosion, the two pieces, they might be unequal. They might sort of fly off in different directions. But if we find the parallelogram made by the velocity of one piece and, well, the momentum of one piece and the momentum of the other piece, if we add them according to the parallelogram method, the sum needs to have the same, it's the same momentum after the explosion as it was before. And that's it. Next class, we will work to apply some of these ideas. And maybe we'll work through an example together, and then there will be some activities for us to work on in development teams. Thanks, everybody. See you next time.